Having learned about the formula of DFT and the representation of the DFT and IDFT as a linear transformation using vectors and matrices, let us now test the understanding of the topic. Let us solve a couple of numericals. Let us consider a very simple situation wherein you are asked to compute the n-point DFT of a sequence x of n, which is 1, 2, 3, 4. This discrete time sequence is having length capital N, which is equal to 4. In the problem, if they mention that explicitly you have to calculate the DFT for 4 points, it is understood that the capital N to be assumed will be equal to 4. Rather, if the question states compute the n-point DFT, then we are expected to count the number of inputs and perform the calculation for that particular length. In this case, the length happens to be 4, so we have a possibility of doing it for n which is equal to 4. Always go with the number which is provided. When it is not provided, you perform the calculation for the number of points equal to the length of the sequence. Now, as we understand from the data, x of n is a sequence which is described for small n, which is between 0 to 3, because the total length is 4 and indexing starts from 0. So the index, that is n, for the first point is actually 0. The index for the second point is 1, the index for the third point is 2, and the index for the fourth point is called as 3. The first method we will try out is called as the analytical method, or it's also called as direct method. The direct method relies on the direct application of the formula of the DFT. We have learned that from the definition of the discrete Fourier transform, DFT of x of n is given by x of k equals summation n lies between 0 to n minus 1 x of n into w into the power of kn, where the k value is between 0 to n minus 1. Since the problem explicitly provides you with the value of n which is equal to 4, and in the absence of that information we said it is based on the number of points of the input. Therefore, the above equation can be modified slightly by inserting the value of capital N, which is equal to 4. Then the equation becomes x of k equals summation n between 0 to 4 minus 1, that is 3, x of n w4 in place of capital N, it is 4, raised to kn, and the k value to be solved is between 0 to n minus 1, which results in 0 to 3. In the next step, let us expand this summation by inserting the various values of n. The first value is x of 0, therefore x of 0 is multiplied by w4 to the power of 0. Next term, n value becomes 1. X of 1 into w4 to the power of k plus x of 2 into w4 to the power of 2k for n which is 2, and the last term which is n, that is the upper limit which is 3, is x of 3 into w4 to the power of 3k. So we observe that in the DFT equation x of k is described in terms of the value k. N is not featured in this equation after we perform the substitution, correct? After we substitute, n is no longer there, and it is a equation which has all the powers of k. So here we have the multiplier of k is 0, here the multiplier of k is 1, here the multiplier for k is 2, here it is 3. So we can believe it to be a series with the powers of k. Now, Since we are aware that the inputs are x of 0, x of 1, x of 2 and x of 3, the corresponding values are x of 0 is 1, x of 1 is 2, x of 2 is 3 and x of 3 will be 4. Let's do the substitution now. So substituting the values, inserting the values in place of the inputs, we get 1 plus 2 times w4 to the power of k plus 3 times w4 to the power of 2k plus 4 times w4 to the power of 3k. Now this equation has to be solved taking the value of k, which is 0, 1, 2 and 3. But before we proceed for the solution, we should find out what are the different Twiddle factor powers that we require. Let us learn how to compute the Twiddle factor powers. The first way how you can calculate the Twiddle factor power is by considering the unit circle on the complex plane. Now this fact results from the notation of w of n in the exponential form, which is e power of minus j2 pi by n. Now we know this is in the complex form. In this complex form, the amplitude is 1 and the phase angle is given by minus 2 pi by n. Therefore, since the amplitude is 1, on the complex plane horizontal axis is called as the real axis and the vertical axis is called as imaginary axis. We draw a circle whose radius equals to 1 and this circle is referred to as unit circle. The reason for drawing unit circle is that the amplitude of w of n is always 1. Now what varies is the phase. The phase angles are obtained on the basis of the value of n. So if n value is 4, then we have to substitute n is equal to 4. It becomes minus 2 pi by 4. Therefore, when the value of n is 4, the entire 360 degree or 2 pi will be divided into 4 parts and we end up with 4 different points. Therefore, now let us perform the Twiddle factor calculation. Generally, whenever you are solving for n is equal to 4, we have to compute the first 4 powers of the Twiddle factor. And the first 4 powers of the Twiddle factor will be w4 to the power of 0, w4 to the power of 1, w4 to the power of 2 and w4 to the power of 3. I repeat, for n, capital N, which is equal to 4, it is sufficient to calculate the first 4 points of Twiddle factor, which is w4 to the power of 0, w4 to the power of 1, w4 to the power of 2 and w4 to the power of 3. But for illustration purpose, we have gone a little bit further just to show you the entire way of finding or calculating the Twiddle factor. So the value w4 to the power of 0 is located on the right side of the real axis. So you can see on the real axis, we can find a point. This point we will take as a reference and this point corresponds to the power, which is 0. And the answer we get is 1, since the radius of the circle is 1. Next, for DFT, we will move in the clockwise direction. As we have learned, for n is equal to 4, we have to divide this circle into 4 equal parts. So the next part will be lying below the imaginary axis. So where does it intercept? The value is minus j. Next point is the other side of the real axis, negative side. So the answer is going to be equal to minus 1. And the final point is above the horizontal. So we get the imaginary value, which is equal to j. So the 4 values that we required are 1, minus j, minus 1 and plus j. But if at all you wanted to continue further, we have to be aware that Twiddle factor is periodic and it has a period equals to capital N. That means that after we have done computation for the power 0, 1, 2, 3, the process will continue like that. For the next power, which is 4, it is actually the same point. Therefore, W4 to the power of 4 is equal to W4 to the power of 0. The next point also corresponds to the power 5. Next will be 6, next will be 7, and like this you can keep on calculating the different Twiddle factor powers. So we can observe that the difference in the powers here is 4, which is equal to the period. Hence, WFN is said to be periodic with a period of capital N. Now, for this particular numerical, I think the first 4 points are sufficient, so we can stick to that. Another alternate method of calculating Twiddle factor is by substituting in the formula. Since we are aware that the formula is Wn is equal to e power of minus j2 pi by n, we can insert the value n is equal to 4, then we get W4, which is e power of minus j2 pi by 4 by inserting the value of n is equal to 4. Simplifying, you get e power of minus j pi by 2. Now, you have an option of calculating the different powers. So this value raised to 0, answer is 1. The next, the value raised to 1. This can be solved by using Euler's relation. So this becomes cos pi by 2 minus j sin pi by 2, because e power of j theta is cos theta plus j sin theta. So therefore, when you solve it, the answer becomes minus j. The next power will become 2. So 2 and 2 cancels. You have e power of minus j pi, which is cos pi minus j sin pi. Answer is minus 1. Next, when you put the power as 3, you get e power of minus j3 pi by 2, which is nothing but cos 3 pi by 2 minus j sin 3 pi by 2. Answer is equal to plus j. So using this formula also, you can calculate the values of Twiddle factors. For n is equal to 4, the first 4 powers or first 4 values are sufficient. Or alternatively, you can show it on the complex plane in this manner for n is equal to 4, and you can easily find and remember the values of Twiddle factor. For DFT, the direction of consideration will be clockwise. Now that we are aware of the various Twiddle factor values, let us insert those values in the equation that we had depicted above. So now we are aware of the numbers. K has to be solved for 0, 1, 2 and 3. So let's consider the value of k equals to 0. Naturally, all these powers will become 0 and the value becomes 1. So x of 0 is nothing but the sum of the inputs 1, 2, 3 and 4. And here we have calculated the sum and we got the answer. The result is 10. For the next step, we have to insert the value of k is equal to 1. When you insert the value of k is equal to 1 in the above equation, we get x of 1 is equal to 1 plus 2 times W4 to the power of 1, 3 times W4 to the power of 2 plus 4 times W4 to the power of 3, and we know from the various methods that the values are minus j, minus 1 and plus j respectively. Substituting those values, simplifying, we get the result as minus 2 plus 2j. Similar calculations are performed for k is equal to 2 also. Here we are inserting the power which is 2, 4, 6 because k value is 2, and again substituting the value gives you the answer which is minus 2. Please note students, W4 to the power of 6 and W4 to the power of 4, although if you didn't calculate, it's easy to calculate it from periodicity. Okay, so we know that W4 to the power of 4 is same as W4 to the power of 0 because the period is equal to capital N and capital N here is 4. So, and similarly W4 to the power of 6 will be same as W4 to the power of 2 whose answer is equal to minus 1. Hence substituting all the values and simplifying, we get the answer. Correspondingly, for k is equal to 3, the powers will become 3, 6, 9, etc. Substituting the respective Twiddle factor values and simplifying gives you the result minus 2 minus 2j, and hence finally we have to tabulate whatever we got. Therefore, the final answer is the frequency domain representation capital X of k, which is equal to 10 minus 2 plus 2j minus 2 and minus 2 minus 2j. Let us try the same problem. using the second method called as matrix method. We had developed the concept of DFT as a linear transformation. So we came across the equation capital X of n is equal to Wn into small x of n. Capital X of n will be the output vector and small x of n is the input vector. Here we are assuming both are column vectors with n elements in it. Therefore the dimension is n cross 1 respectively, whereas twiddle factor is an n cross n matrix. So in this context, in our problem, we know the value of n is 4. So we can write the above as x of 4 is equal to W4 into x of 4. Suppose we go with the row notation, we remember that the positions of the small x and W should be exchanged to satisfy the rules of matrix multiplication. Therefore, x of 4 is written first, followed by W of 4. Let us follow this method while we are solving this particular numerical. So first comes the input vector. So x of 4 represented in the row form is the matrix 1, 2, 3, 4. Next comes the twiddle factor matrix. Now how do you arrive at the value of twiddle factor matrix? We shall learn that. We are aware that for n is equal to 4, it should be a 4 cross 4 matrix, and first row and first column always comprises of values 1s. The remaining values can be easily written by remembering that the row number 2 are powers which are multiples of 1, next multiples of 2, and next is multiples of 3. Therefore, the values you can observe here are powers 1, 2, 3, and here we get 2, 4, 6, and last we have 3, 6, 9. Now, to proceed with the calculation, we need values of these. Therefore, let us insert values. So, since we know about the periodicity of the twiddle factor, we can easily compute all the values starting from W4 to the power of 1 till W4 to the power of 9 by using periodicity. So W4 to the power of 9 is nothing but W4 to the power of 5 plus 4, which is equal to W4 to the power of 5. Now when we don't know what is W4 to the power of 5, W4 to the power of 5 can be written as W4 to the power of 4 plus 1, which is same as W4 to the power of 1, which is a familiar value. So easily we can get the values for various powers, and inserting those values, we obtain the twiddle factor matrix for n is equal to 4. See, while simplifying using periodicity, we now observe that the twiddle factor matrix is actually symmetric. So W4 to the power of 1, W4 to the power of 1, W4 to the power of 3, and so on. So this is a symmetric matrix. Now substituting the various values, we get the twiddle factor matrix to be first row, first column, all ones. Then we have minus j, minus 1 plus j, minus 1 plus 1 minus 1, j minus 1 minus j. So we can easily remember this pattern and apply this directly when the problem is asked. So it is symmetric about the principal diagonal, which I have indicated here. And the values you can see is very simple. So at the center we have all ones. So the center middle one is plus 1. The surrounding ones, they are all having minus sign. Whereas in the corners we have j. The principal diagonal has negative, whereas the other one we can see is plus. So this way we can remember the pattern and easily apply it whenever required. The next step would be performing the matrix multiplication. We are aware how to multiply. The row is multiplied with the column. So after multiplying, we should be able to calculate the answer, and the answer will appear to be in the form of row. Because input was a row, output will also be written in the form of row. So here we are doing the operation of multiplying. So first we shall discuss 1 into 1 plus 2 into 1 plus 3 into 1 plus 4 into 1. So that will be the first answer if you simplify it. Next comes 1 multiplied with 1. We are considering the second column. 1 into 1, 2 into minus j, 3 into minus 1, 4 into plus j. Like this, if you continue, we will be able to calculate the 4 different terms. So after calculating the 4 different terms, we get the final answer, which is as shown here. So the result is matching with what we got in the direct method. The answer is 10 minus 2 plus 2j minus 2, minus 2, minus 2j. This numerical discusses about computation of the IDFT. Here again, we will learn both the methods. For simplicity, let's take a sequence called as x of k. X of k is a frequency domain sequence. The inputs given in the problem are 10, minus 2 plus 2j, minus 2, minus 2, minus 2j. So since it's a problem that we just worked out, we are aware that x of n for this should be the answer 1, 2, 3, 4. Now, the problem explicitly says you solve it for 4 points. When the number of points is not mentioned, please consider the length of the sequence and do computation for that many points. First, let us apply what is called as the direct method. In the direct method, from the definition of IDFT, we know the formula. IDFT of x of k is given by x of n is equal to 1 by n times summation k between 0 to n minus 1 x of k wn to the power of minus kn. The value of n lies from 0 to n minus 1. Now, in the given problem, since we are aware that n value is 4, substituting capital N is equal to 4, this expression becomes 1 by 4 times summation k from 0 to 3 x of k w4 to the power of minus kn. Now, we know the difference in the DFT and IDFT equation is the total factor power. There we had positive, here we get negative, and the expression here is actually in terms of n. Therefore, if we expand the summation, we will get a series here which is having powers of n, that to negative powers. So there we got positive powers in terms of k, here we have negative powers in terms of n. So this is expansion of the above equation. Next, as we are aware of the inputs, that is capital X of 0, X of 1, X of 2 and X of 3, let us substitute those values. So substituting the values of inputs, we can observe here we have substituted 10, minus 2 plus 2j, minus 2 and minus 2 minus 2j. So this equation has to be solved considering the value of n 0, 1, 2, 3. That's all, okay? Because number of points is 4. Once again, the task is to find the total factors. Now again, we can take the help of the complex plane, represent the unit circle. We know the entire complex plane is divided into 4 parts. Again, you start with the reference. So the origin is going to be the point on the real axis, which is on the right, which corresponds to the value 1. And from the origin, this time we will travel in the anti-clockwise direction. See, the power in the case of DFT was, for Wn, it was plus. We travel in a clockwise direction. Here it is minus, so the direction we take is anti-clockwise. So remember that for IDFT, we have to travel in anti-clockwise direction. So we can compute easily the first 4 values, which is 1, j, minus 1 and minus j, and the remaining values can be easily calculated following the circle in anti-clockwise direction. Therefore, now let us proceed for the substitution. Now the total factor values here are listed. W4 to the power of 0 is 1, W4 to the power of minus 1 is j, W4 to the power of minus 2 is minus 1, W4 to the power of minus 3 is minus j. Substituting the values now in the equation that we have written above. So when you consider the value of n is equal to 0 and inserting the values of total factor, we end up with the simplification x of 0 is 1 by 4 times. This is the sum of the inputs, because we know for n is equal to 0, all the total factor powers will be 0. So the simplification gives you 4 by 4, answer is 1. For the next substitution, n value is equal to 1. This time we are inserting the value n is equal to 1. So when you put n is equal to 1 here in the previous equation, now n becomes 1 here, and then we get the various total factor powers and inserting those values as shown here. So W4 to the power of minus 1, W4 to the power of minus 2, W4 to the power of minus 3. These values we have to substitute along with the inputs, and we can simplify and get the answer as 8 by 4, which is equal to 2. Similarly, the answer for n is equal to 2 requires W4 to the power of minus 2, W4 to the power of minus 4, W4 to the power of minus 6, which is 12 by 4, answer is 3. For n is equal to 3, the powers are -3, -6 and -9. Again substituting and simplifying, the final answer is equal to 4, and you can tabulate the results of the sequence x of n as answer is 1, 2, 3, 4. The same problem done using the matrix method. So this time we use the inverse formula. The formula says x of n is equal to 1 by n times wn conjugate x of n, provided capital X of n and small x of n are column vectors. This time the input is capital X of n, the answer is going to be small x of n. Input is frequency domain, output is time domain. But if we prefer row, then we have to remember that we have to place the x of n first, then we have to put the total factor to satisfy rules of matrix multiplication. Going with this notation, for n value 4, the expression becomes x of 4 is equal to 1 by 4 times capital X of 4 into W4 star. So star here refers to complex conjugate. That means that in the DFT problem, the total factor matrix that we considered, we have to conjugate. The conjugation means the sign of the imaginary term should be changed. Therefore, the resultant substitution can be written like this. First we have 1 by n, that is 1 by 4. Then we have the input, that is x of k, written in the form of a row. And then we can see the total factor matrix. It's identical to the previous, but please note the sign of the j terms. The real terms will not be affected, only the imaginary terms we have to take complex conjugate. Therefore, on the principal diagonal you can see the j sign is plus and the other j is negative. This is called as complex conjugate. Next, performing matrix multiplication. We can see the steps here after multiplying row with column, respective columns, and we get 4 answers. Answer is in the form of a row. The result is 1 by 4 times 4, 8, 12, 16, and simplifying gives you an answer which is 1, 2, 3, 4, which was confirmed in the previous substitution also. Thank you all.